This is a video for MEI Core Pure Mathematics, Hyperbolic Functions 2, Inverse Hyperbolic Functions, 2.3, Integration using Inverse Hyperbolic Functions. In a previous video, we've looked at the derivative of r sin x, the inverse hyperbolic sine, and found that it was 1 over the square root of 1 plus x squared. So, looking at integration here, we can conclude that if we integrate 1 over 1 plus x squared, we'll get r sin x plus a constant if it's an indefinite integral. Similarly, for r cos x, we found this was its derivative, and therefore if we integrate this, 1 over the square root of x squared minus 1, we'll get r cos x, and again, plus a constant if we've got an indefinite integral. And so we can generalize those further. So we get this integral for 1 over the square root of a squared plus x squared. It's just r sin x over a plus some constant. And the integral of 1 over root x squared minus a squared is r cos x over a, again, plus a constant. Now, remember that these are in your formula book, and you can quote the results as a consequence. And also remember that you may see r sin x as sin to the minus 1 and r cos x as cos to the minus 1, depending on the resources you're looking at. Both of these results are really useful to extend the range of functions that we can integrate, and we'll look at these in the next video. For both of these, notice that the coefficient of x squared is just 1, and we'll actually look at an example a little bit later at what happens if the coefficient of x squared isn't 1. So let's have a look at this. Well, we've got the required integral listed up here for us as though it was in your formula book, and this is really very, very simple. It's this in standard form with a is equal to 5. And so its integral is just simply r cos x over a, so here it's x over 5, plus a constant because we've got no limits, it's an indefinite integral. So let's have a look at this example. It's not quite in the same format as we've got up here. We've got just a coefficient of 1 for x squared, and here we've got a coefficient of 9, so we need to deal with that. To do that, we're going to take a factor of 9 out of the square root. And remember that when the factor 9 comes out of the square root, it'll be a factor of 3. So this will give me 1 over 3 times the integral of 1 over, take a factor of 9 out of this, that'll be 16 over 9 plus x squared dx. And this now is in the same form as we've got up here, but with a is equal to 4/3. And so this becomes just simply 1/3. Don't forget your 1/3 outside the integral here. R sin x over a, so that's going to be 3x over 4 plus a constant because we've no limits. There's that written up so that you can read it a little bit more easily, and here you can see there's the 9 being taken out of the square root, which comes out as a 3, and then we just apply the standard form to this to get our result. So the summary for this then, we've got two types of integral that we can now tackle, one of which is r sin x over a plus c, and the other is r cos x over a plus c, and they are in your formula books, and therefore you can quote them without proof. And secondly, if the coefficient of x squared is not 1, then we take out a factor out of the denominator to get it into the correct form so that we can then use the standard result. And you do that first and then apply the standard result. The next and final video in this sequence is 2.4, Integration using hyperbolic substitutions.